All right, welcome to class, everyone. So I have a headphone on to hopefully cut down on background noise, and I can still hear my mouse clicking in the background. But I'm going to try to do that. I'm using this headset, so hopefully that cuts down on my keyboard and mouse clicking. But yeah, if you want to join in, and again, remember top hat questions that are live do not count for or against you. They're just for fun. So again, if you miss the question, time runs out, or you get the question wrong, don't freak out. Better you get the questions wrong now and take too long on them than on the actual test and your assignments. But yes, you can see the join code up there. Join code 142797. And don't worry, I'll let you know when we're actually using Top Hat. But again, if you want to get ahead of the game, you can start joining right now. All right, so now it's on to our actual lecture. So we're going to talk about more chemistry. And actually, a really good question came up at the end of last lecture. Okay, so let's talk about chemical formulas. So this lists how much of each element is in a molecule. So whenever you have molecular formulas, you always see the a lot of letters and numbers, right? Well, here we have in this atom of diatomic hydrogen gas. Again, what you have is first you have the element, then the number in the lower right corner refers to how many atoms of that element you find in that molecule. So here's how I represented it last class as cartoons, but when you write the chemical formula, again, you have the lower right number refers to the amount of atoms found in that molecule. So element, molecule, compound, we played this game last lecture, right? So again, helium is an element, and sodium chloride, it's a compound, definitely a compound, but is it a molecule? So we know this is a compound and a molecule, and we know that this is an element and a molecule. Now the question came up, so sodium chloride, when it's actually in the body, it breaks apart. It's what we call dissociates. So it starts to like all the sodium ions and the chloride ions, they actually separate and they're floating around in the water. So your body, in terms of solutions, the main solvent, the main solution in your body is water-based. So these sodium and chloride ions, they're not really bound together like we have in this picture. So it's kind of funny. Is sodium chloride a molecule? So does the molecule, so because in the body it's not really typically just one sodium, one chloride stuck together. And plus we'll get to why they're a special type of bond. They actually don't share electrons, but we'll get to that real soon. Okay, so sodium and chloride. So definitely a compound, but is it a molecule? So the Martini says that a molecule has to be a chemical structure containing two or more atoms that are bonded together by sharing electrons. Now, OpenStax, on the other hand, it goes a little more roundabout, not really saying like, so what you have to say is two more atoms held together by chemical bonds. That's what you call a molecule. And a bond is a weak or strong electrical attraction that holds atoms in the same vicinity. So the thing about sodium and chloride, you see that sodium is positive, but chloride is negatively charged, right? So there is electrical charge holding them together. But the thing is that OpenStax doesn't say whether sodium chloride is compound or molecule. So again, it's like, is it a molecule or not? And it's funny, if you go, I tried looking this up, and then it's very interesting. So here's one that says that, okay, because it's not made out of single discrete molecules, in other words, it's saying that sodium chloride, when you find it, isn't typically just one sodium ion and one chloride ion stuck together. So you never really find that. That's why it's argument that it's not a molecule. Whereas Quora, these are people's opinions, but again, do not use this as a reference. Like, I don't think too many people have used it as a reference in PackBack, but if you're taking any sort of other class where you write a lot of essays and reports, do not use Quora as a reference. You will guarantee your professor is going to take points off. But it's interesting. So like this person says like a molecule is defined as a group of atoms bound together. So they said that ionic compounds are made of molecules because they repeat. But someone else says like, oh, maybe it's covalent bonds. So they go by the covalent definition. And this person says like, okay, it's like ionic compounds are crystals of infinite cations and anions. So different opinions. And again, Reddit is not a primary source either, but it's interesting. It's like, okay, is it molecular bonds or covalent bonds, or is it ionic bonds? Do they count as bonds that hold a molecule together? And over here, now, so it's funny, like basically I even asked two of my friends who have degrees in chemistry, and they actually started arguing with each other. They said like, well, in theory, if you had one sodium and one chloride, and it was so funny. They both had PhDs, but they couldn't agree. So thing is that it's the thing. Even though it's science, it's all fact based. There's a lot. Sometimes there are debates. Sometimes people have different opinions, and I actually agree with this person down here. It's a matter of semantics, not chemistry. So this is what I'm getting at with this whole debate right here. So will you be, I'm sure what you're wondering is like, one, will you be tested on this? No. Two is that, okay, whenever there's a debate, I go with what is in common between the two sides. And what we see common between the two sides is that a molecule, in both your textbooks, and pretty much everybody agrees that a molecule has two or more bonded atoms bonded together. Now, whether the ionic bond that holds a single, like if you had a single sodium and a single chloride together, whether that's considered a bond that qualifies as a molecule, I'm not getting to that debate. So there's no consensus on that, but it seems like more toward like it's not a molecule because it's typically a crystal if you do find it in a solid form, and doesn't really form crystals in physiological conditions. But so I also don't want you carrying this on to chemistry. Chemistry, go with the chemistry textbook's definition of a molecule. Do not say Dr. Higa said that it's a molecule, it's not a molecule or whatever. So again, whenever there's a disagreement, I tend to go with what is in common. Again, do not carry anything like this into your other classes. Again, this is the main point. A molecule has two or more bonded atoms held together. So this leads into chemical bonds. What is a chemical bond? So I think this is a great part to start. So ionic bonds are like we find in sodium chloride. These are between cations and anions. So cations are positively charged ions, anions are negatively charged. So the mnemonic I like to use, if you're a cat person, a cat is a positive influence in your life, right? So cations are positively charged, and by process of elimination, anions are negatively charged. So covalent bonds, these are strong bonds that share electrons. And then strong bonds that share electrons, and I'll get more into that. So polar covalent bonds are a subtype of covalent bonds. So we'll get into that. And hydrogen bonds, these are weak partial positive and negative attractions. So again, the funny thing is that these all involve electrons to one point, but whether they involve the electrons, the way they handle it is different between these types of chemical bonds. So ionic bonding. So the thing about bonds, that's why I said like atoms and chemicals are kind of like people. Bonds are relationships between atoms, but just like how you have different relationships with your parents, with your friends, with your significant others, there are different types of bonds between atoms. So what's ionic bonding? So like in sodium chloride, remember how I told you like some atoms have like particular preferences in the amount of electrons they like to keep? Same with sodium and chloride. So things that if you just had the equal amount of protons and electrons for sodium, it actually likes to get rid of that extra electron. It's more comfortable having one less electron than its protons, and chloride actually likes having one more electron than it does protons. So again, what happens if you transfer one electron from sodium to chloride? Well, you have 10 electrons on sodium and you have 18 electrons on chloride. So what's the charge on sodium? Again, remember which is positive, which is negative. Protons are positive, electrons are negative. So what's 11 minus 10? That is 1. So that's why sodium ions have a positive charge. They are cations. Whereas chloride, again, these are negatively, so chloride, you have 18 electrons. Electrons are negatively charged. So 17 minus 18 is, again, negative 1. So again, this is why sodium and chloride have positive and negative charges as ions, respectively. All right, so again, the thing is that it's just like magnets. Like what you have here, that even though they don't, one electron was transferred from sodium to chloride, they're attractive due to the positive and negative charges. So you've heard that term opposites attract. Well, that happens in physics. That also happens in electricity and electrochemistry. So if you have a positive charge and a negative charge, they tend to they attract each other. All right, so covalent bonds. So how are these different from those bonds? Okay, so here we have two hydrogen atoms. And remember that if it's not a proton, say these atoms still have their electrons. So what happens is that hydrogen likes to share. So the thing about electrons, they like to be paired up. And if you're taking chemistry, you'll get more into detail about why they like to pair up. But just know that at this level, they like to pair up. But covalent bonds, what we have is that now instead of ripping off an entire electron from one atom to another, they're actually sharing the two electrons between each other. So they initially start with one, but they're kind of pulling their resources together. And here we have two oxygen atoms, and they actually have more electrons. I'm just showing you two for simplicity's sake. But notice that they're now sharing electrons. Again, these electrons like to form pairs. So polar covalent bonds, the thing is that with these bonds, they're equally sharing that pair. So notice that they're in the middle and that they're not, neither atom on the left or right in these diagrams is holding on to these electrons more than the other. So this is what you call a non-polar covalent bond. Whereas in a polar covalent bond, what happens there? So what happens then is that here we have H2O, aka water. So this is a cartoon. Again, I'm not showing all the electrons for simplicity's sake. But what happens with water, the thing is that oxygen is a little greedy in the water molecule. It actually likes to hold on to the electrons a little more. So remember I showed you that model where electrons are actually flitting about those electron clouds and shells? Well, the thing is that when you have two hydrogen atoms and bound to oxygen in a water molecule, the oxygen actually holds on to the electrons a little, on average, for a longer period than the hydrogen atoms. So it's kind of like, say you have everyone's social distancing in the dorms, but say you have a roommate or you have a sibling and you have a toy and your sibling or you like to hold on to that toy a little longer. So same with the oxygen. The oxygen is a little greedy. It likes to hold on to those electrons a little longer. Now, this is why you need to know electrons have a negative charge. Because oxygen holds on to electrons a little longer than the hydrogen atoms, it tends to be it's not a complete negative charge. It's not like you have in an anion. But because electrons hang around the oxygen atoms a little longer, there's a slight negative charge in an oxygen atom in a water molecule. And because these four hydrogens, they have less time with the electrons, they actually kind of lose a negative charge. So that it kind of flip-flops. They become slightly positive. So it's not a full positive charge. It's not a full negative charge. But this unequal sharing, that's what they mean by polar covalent. So you're still sharing electrons, but compared to the previous examples with diatomic hydrogen and diatomic oxygen gas, these are unequal in terms of how much time the electrons are shared between the atoms. Now, why is hydrogen bonding important? So the thing is that with these positive and negative charge, remember, positive attracts negative, negative attracts positive. So what we have here is that we have all of these hydrogen bonds. So the slight positive charges on the water molecules are attracted to the negative charges right here. And that's what we have here. So electrons are not shared in a hydrogen bond. This is a key difference in terms of so remember, ionic bonds, one electron is ripped off of the other and they're attracted just due to the positive negative charge. Covalent bonds, you do have a sharing of electrons, and if it's nonpolar, it's shared equally. If it's polar, it's shared unequally. But hydrogen bonding you do have attraction between positive and negative, but no actual electrons are being shared. It's just due to the slight positive charge, in this case, on hydrogen in water, and the slight negative charge on oxygen in water. So again, these do not share electrons, but electrons are the underlying cause. So it's due to the slight positive and slight negative charges. And again, don't carry over that parentheses positive and negative. I'm just telling you that it's not a full-on positive and negative charge in these polar bonds or polar covalent bonds that are driving the hydrogen bonding between water molecules. So the thing about hydrogen bonds, they're actually, compared to especially covalent bonds, they're very weak. So they're kind of like, let me see, have like magnets. So things that magnets also have positive and negative poles as well. So things that magnets, they stick together, right? But the thing about magnets is that they're easy to break apart. So one by one, they're not very strong, but they're useful for things sticking to each other. Same with these molecules. A lot of molecules, especially proteins and how they build when you fold protein and assemble protein, or how many of the molecules in your body bind to each other. Hydrogen bonds are there, but what happens if you have a lot of hydrogen bonds stuck together? So hydrogen bonds. So here is a pull, right? So the thing is that it's pretty easy to stick your finger into a pull, right? But what happens if you have all these water molecules and all these hydrogen bonds stuck together? Well, the thing is that what happens if you say, if you just have a cup of water, it's easy to put your finger in it. But what if you try to enter the water like this? So is that as painless as sticking your finger in a cup of water? Again, you have all that energy, but the thing is that when you have a bunch of hydrogen bonds stuck together, it can form a much, much stronger overall structure. So this is why if you hit a body of water like that, it's going to sting because you have all those hydrogen bonds in that body of water right there. Okay, states of matter. This is like, don't worry too much about this. It's in the Martini book. But again, water has many forms depending on, again, liquid is the main form in your body. Again, unless you'll be dead if the water in your body is solid, and it's ice and gas. And steam. This is like, okay, there is water vapor, but again, you won't find the solid part. We're just talking about states of matter. So again, solid, the volume and shape are held and are relatively constant at atmospheric. In other words, just our everyday environment here. And physiological, so inside your body. But again, this is different things. So again, changeable just meaning like, okay, liquids in your body are relative constant in volume, but if you pour them from, say, like from one container to the other, it takes the shape of the container. That's what it means by changeable. And gas, again, volume can depend on pressure. So if the thing about gases is that they can be compressed. That's why, like, if you go to Starbucks, they have the whipped cream. I have all that nitrogen gas in that canister. So if you have like a compressed gas or like the one, let's see, I don't have it near my desktop, but you can compress gases, right? That's why you have those gas cylinders. And the thing is that gases take the shape of whatever's containing them. That's pretty much what I'm getting at here. All right, so we talked about chemical bonds. So let's talk about chemical reactions. So chemical reactions are whether those bonds are formed or broken. Remember, I told you that chemical bonds are like relationships between atoms, just like we form relationships with each other. Just like we form relationships with each other, unfortunately, sometimes relationships can be broken. Same with kind of chemical bonds. So reactants, that is a key word meaning that starting materials. Oh, and actually, I think I mentioned this before. If you see bold words, these are key vocabulary words I want you to know. And products, these are the end results. Again, it makes sense. You have things that react together, they produce something called a product. That's the end result. Now, metabolism, this is a general term. Different textbooks have different definitions, but metabolism is the sum of basically all the chemical reactions that are occurring in your body right now. So all the reactants, products, whether you're building things up with anabolism or breaking things down with catabolism, all of those together, these are metabolism. So again, metabolism is basically calling your whole entire body a chemistry set. And the entirety of that chemistry set, that's metabolism. All right, so then you have a decomposition reaction. So when something decomposes, like say you have food decomposing on the counter, that's breaking down, right? So this is also known as catabolism. So here we have food and oh shoot, yeah, it starts out nice, but it's breaking down. So it's decomposing. That's catabolism when you have these reactants and they're breaking down into other products. Whereas the synthesis reaction, anabolism. So synthesis, you're making something new, right? When you synthesize something, you're creating something. So when you think about, when you think about anabolic steroids, what do you think of? You think of these people who use them that try to build up muscle, right? So anabolism is building something, it's synthesizing something new. Whereas decomposition and catabolism is breaking apart. So these are opposites. Now synthesizing, again, here we have a 3D printer. So what are you thinking? that filament and you're building something new out of these tiny little drops of plastic, right? So synthesizing something new. Now exchange reaction, just like what it sounds like. Exchange, you give something and you take something. So you get something quid pro quo. You get something for another thing. So it's not quite, it's not decomposition, it's not synthesis. You give one, you give some, you take some. And reversible reaction, it sounds like what it sounds. So it can go both ways. It can go the reaction can go one way from reactant to products, but the products can also become the reactants and make the original reactants the product. All right, so again, this is analogy time or metaphor. I don't know, I'm not an English major. But here's what it's like. So remember, you have A and B. These are just theoretical chemicals, right? So these are your reactants, and now they're forming a product. So remember how I said chemistry is like relationships, right? This is a synthesis reaction. Why? You're making a new product out of two separate parts. So it's like synthesizing a new relationship. So synthesis reactions, you have two reactants, two or more reactants, and you're producing a final product together. So this is a synthesis reaction. Again, you have separate components, but they're making a new product, a new novel product. Now, what's the opposite of a synthesis reaction? A decomposition reaction. Again, you have one product, now you have one reactant, now it's breaking apart into two different products. So decomposition reaction, remember decomposition and synthesis are opposites. So instead of having a relationship and forming a new one, now you're breaking that bond. You're breaking that initial, so the reactant, you originally had these two atoms paired up and coupled together, but now, oh no, they broke apart. Now they're into different products. Their relationship decomposed. So again, this is a decomposition reaction. All right, so then now this is another. So what we have here is that now we have four players in play. But what's happening here? So these are our initial reactants, but what is the product? Well, this is the overall chemical reaction. So you notice that they do have two pairs and bonds in the beginning, but now something did change. You still have two bonds in the end, but something exchanged, right? So actually, I think some of you, especially you're the freshmen, you probably don't remember this, but when you were kids, these sort of like trashy shows happened all the time. I don't know if you've ever seen that God Warrior meme. Actually, she's a fascinating story. You should see Wang's video on it. But the thing is that they had all these things called like trading spouses, wife swap, where they have married couples and they exchange partners for a week. And this was before all the Kardashians and everything became reality TV, like before History, Discovery, and all those channels became reality. And we started following random housewives in random cities. But anyway, so exchange reactions, what we have here is kind of trading partners right here. So again, you have two different bonds right here, but somehow they start trading partners, and you end up with two different couples. So this is exchange reaction. Or actually, it's kind of like, so at my high school, it was very interesting. So the band, it was kind of the dating situation within the band. I wasn't part of the band, but it was interesting because all the people in the band were kind of like dating each other, and if the couple broke up, they were only allowed to, it was an unspoken rule that they were only allowed to date people within the band. So they're exchanging partners all the time. And yeah, and I actually got in trouble when I started dating someone from the band. They're like, but he's not part of the band. But yeah, this is a silly high school drama. But yeah, exchange reaction, you have these kind of swapping of partners between these bonds. Again, these are reactants. The products, you still have the same amount of bonds, but notice that the products, in terms of the chemicals, this is not the same as this or this. This is not the same as this or this either. So you did have a change in these relationships and bonds. Now, here we have, okay, so you might know a couple like this, and who knows, you might be one of these couples. But what do we have here? Getting together, breaking apart, getting together, breaking apart, getting together, breaking apart. So you might know a friend like this who's in that. I had a friend like that, my roommate in college. Yeah, they were in a relationship like that. But 1 week they're together, next week they're apart. 1 week together, next week apart. It flips flops between this. This is what you call a reversible reaction. So what we have here is both synthesis and decomposition, but it can flip-flop both ways. So this is a reversible reaction, typically represented instead of just a single arrow pointing one direction. Notice that this is a double arrow. Sometimes the double arrow is split into two stacked arrows that are pointing in opposite directions. But again, and thing is that the reactants can become the products depending on which way you're looking. So again, to summarize these chemical reactions visually, this is again the synthesis reaction, this is a decomposition reaction, this is an exchange reaction, and this is a reversible reaction. Again, notice that the products are all different from the initial reactants, but were there bonds made, were the bonds broken, can this reaction go both ways? That's the difference between these four general categories of chemical reactions. Okay, finally we get to top hat. So again, let's get to top hat. And again, don't worry, this is just for fun. If you don't get your answer in time or if you get it wrong, it's perfectly fine. All right, so let's see how people did. And okay, whether it's anabolic, catabolic. So most of you were kind of split. Or so, a lot of you said, most of you said it's a synthesis reaction. Again, you're making a new relationship. You're making a new bond. It is a synthesis reaction. Now, is it anabolic or catabolic? Well, again, anabolic and synthesis. So anabolic, you're building something up. So again, you're building a new bond. So it's both anabolic and synthesis. It's not catabolic or decomposition because that's breaking things apart. It's not reversible because look at the arrow right there. I'm only showing one direction. So if there was double-sided, a double-headed arrow, it would be reversible. Okay. All right, so it looks like a lot of you got that. So back to our presentation. Okay, so why am I talking about anabolic and catabolic? So again, look at this. So anabolic are built. So what we have here is a very abstract, but a very simplified version of showing how anabolic and catabolic reactions occur in terms of metabolism of food. So here we have, again, food is being broken down. This is why it's catabolism, but notice that's releasing energy. Whereas when you're building something up from these small components and making something new, this requires energy. So why is it very important? Well, the thing is that when you make and break bonds, they can release or store energy within those bonds. All right, so the thing is that why am I talking about energy? So this is a thing about, especially with physiology, you'll see a lot of graphs. If you don't like graphs, you have to learn them, okay? Because the things is physiology and physiologists, they love making graphs. So what we have here is this. As a reaction, this is just time. As a reaction progresses and you're kind of just setting a timer and waiting. So this is the amount of energy you need to go from one place to another. So you want to go from reactant to products, but notice that there's a little hill right here. So there's a little cost that you need to have a little bump in energy to push a reactant over the hill into products. So it's like if you're making chili or a soup. Can you just cut things and throw them all together and expect the mixture to just sit there and then all of a sudden you have chili just if you wait there long enough? No, you have to kind of add a little heat. You need to cook it. You need to add a little energy for things to melt together. So reactants and products, especially if it's one that requires activation energy, it needs a little energy to get over that hill. Or if you're local and you live on the west side, which takes more gas or energy? To drive up from King to University, or if you need to drive up Makokilo Drive, or St. Louis Heights, or Wilhelmina Rise. So again, the bigger the hill, the more energy you need, right? Same with reactants and products. So the thing is that you want something that makes it easier so you don't have to jump. If you want a reactant to form a product quickly, you want to make this part a little easy. You want to kind of flatten that hill a bit. And this is the OpenStax version. So notice that, again, the bigger the hill, the more energy it requires. And this is one of the things, like the trade-offs between OpenStax and the Martini, is that I noticed that Martini has a lot of detail, but sometimes OpenStax is a little simpler, but does a better job of kind of conveying things. Martini likes to have very dense images that shows everything at once. So the thing is that chemical reactions need energy. That's the main point I'm getting at here. So say this is like a chemical reaction. Here we have our initial reactant. We have a closed bottle with a bottle cap. What the product do you want if you want to drink that bottle? You want to somehow open that bottle and have a bottle cap. And these are our products. You want to go from point A, this closed bottle, to the open bottle and the bottle cap. So the thing is that, can you open it just by brute force? Yeah, you can. I mean, I never tried it. But say you're trying to open this just without any other tools. You're trying to open this with your bare hands, and it's not one of those screw cap bottles. Well, after a lot of energy and potentially a lot of blood, you can open it, but that requires a lot of energy, right? What can you use to make your job easier instead of opening it with your bare hands? You can use... Oh, actually, let's rewind a bit. Let's go to Top Hat. So let's use this analogy. If this were a chemical reaction, which word would describe it better? Decomposition or synthesis? Okay, let's see what everyone said. So it seems like the majority of you said it's decomposition, and the majority of you would be right. Why is this more like a decomposition reaction? Because again, you're starting with two things that are held together initially, so just one thing, but this bond was broken, the seal was broken, so now you have two products. So if it's like the AB breaking apart into A plus B, so it doesn't matter how small that product is, it doesn't matter the size or how much it is. If you're breaking bonds, that is a decomposition reaction. So back to ourselves. So things that, what can you do to make it easier? So think about enzymes. Enzymes, they have multiple properties. We'll get to a list of that later. But things that, what do you want? You want that open bottle. So you want to go from here and somehow this initial reactant. And the thing is, enzymes, these actually make these reactions easier by kind of lowering the energy. So you still need to use energy to open a bottle with a bottle opener, but not as much energy as you would with your bare hands. So by using something like an enzyme, if your body uses an enzyme, it can actually make reactions easier to occur by lowering the energy. So it still requires energy, but not as much without the enzyme. So this is why you have easier. So just like how the bar opener makes this whole reaction easier, same with enzymes. They make reactions easier to occur. So it speeds up the overall rate of the reactions. Again, that's more of like a Chem 161 topic, but this is why I like to think of it. It makes chemical reactions more efficient. Why? Because again, you're not spending as much energy as you would without the enzyme. Therefore, this reaction can occur at a faster rate. So say you had a bunch of bottles to be open, and you had a race between someone using their bare hands versus someone using a bottle opener. Who's going to win? Who's going to have more open bottles? The one with the little bottle opener, right? Same with a chemical reaction with the enzyme versus without. The one with the enzyme is going to occur at a faster rate. So again, enzymes make versus the bottle opener, or versus just opening with your bare hand, the bottle opener makes it more efficient. Same overall reaction, you still have the same reactant, you still have the same closed bottle, you still have the same products, but how you go from point A to point B, that's the difference. And how much energy you spend, there's a big difference there. Okay, so again, this is how it is with activation energy and the martini version of this. But again, if we want to go using that analogy right there, this is what we have here. Again, you're going from the same reactant, same products, but depending whether you're using an enzyme or whether you're not using an enzyme, there's a big difference in the amount of energy you need to actually go from the reactants to the products down here. All right, so things that enzymes are what you call catalysts. Okay, so catalyst is more of a biochemistry term, so don't worry about that so much. I mean, but things that know that they are catalysts, there are many other catalysts, but yeah, just know that they are a type of catalyst. So things that catalysts help chemical reactions. So not all catalysts are enzymes, but enzymes are catalysts. It's one of those like logic things. So things that most enzymes are proteins. There are some enzymes that are a mixture of ribonucleic acids and proteins, but again, in general, if you took all the enzymes that are known in the human body, most of them are protein-based. And enzyme names typically end with ASE. There are some exceptions, but if there's a protein or any sort of that ends with ASE, it most likely is an enzyme. So this is way you can know something's an enzyme. All right, so here's the enzyme, and what we have here, these again are reactants, and you're having a product. So notice that you're taking two reactants, bonding them together, and making a final single product. Synthesis, decomposition. Again, you're making a new product, you're forming a new bond, so it is synthesis. And this is the open stacks version, and again, it's also showing a synthesis reaction in a very similar way. All right, so another analogy you can use. So you have papers and staples, right? So what we have here is that these are reactants and an enzyme and a product. So the product is you want these papers stapled together using the staple. And the enzyme you might use in this case is the stapler, right? So things that, is the stapler actually part of the final product? You notice that's not actually not part of the final product, but does help this go from this point A with the reactants to this point B with the product. Oh, so another top hat question. If this was a chemical reaction, which word would describe it better? Decomposition or synthesis? All right, let's see how everybody did. So most of you said it's a synthesis reaction, and most of you are correct. Again, you're forming a new bond. So again, you have multiple reactants and you have a final product. So this is what I'm getting at here with this whole analogy. So yes, it is a synthesis reaction, but what did you notice? Again, you notice that the stapler was not altered. It did change shape. It did have some action, but it did not become part of the final product. So that's another key part of an enzyme. Enzymes are not consumed by the whole overall reaction. You do have consumption of reactants when you're finally, so as you start stapling more papers together, you have fewer staplers, you have fewer unstapled papers. So that's why enzymes are not consumed by the reactions. They do not become part of the reactants or products. Otherwise, they would be reactants and products. So the things that, can you go from this product in this example to the reactants? So you can insert a way, even though it will be kind of wrinkled. What you have for the enzyme that does that is the staple remover. So you can go from initial stapled papers to a stapler that will be bent out of shape, but you will have products. So you go from something that was intact and breaking it apart into smaller products. But is this the same enzyme as what we had before when we went this way? Remember, it's a totally different enzyme, right? So not quite yet, jumping the gun. So things that you can have enzymes that do synthesis, you can have enzymes that do decomposition, and sometimes you can have enzymes that do both ways. They can actually cause a reversible reaction by either doing the synthesis part or the exact opposite decomposition part. So the thing is that you need different enzymes for different tools that might do the overall same reactants and products. That's why I kind of use this example. All right, next top hat question. All right, so which one of these is most likely to be an enzyme? All right, let's see how everyone did. So yes, most of you answered catalase and most of you are correct. Again, if it ends with ASE, dead giveaway, it's most likely to be an enzyme. And again, remember, not all enzymes have ASE, like pepsin is one of the examples I can think of, or like trypsin. Like some of them do not have ASE, but if you see those last three letters, it's a dead giveaway most of the time. All right, and speaking of catalase, so it is an enzyme and it catalyzes the following chemical reaction. What type of chemical reaction is it? Okay, most of you said that's a decomposition reaction. Otherwise, like it's kind of evenly spread among the others otherwise. And most of you are correct. It is a decomposition reaction. Why? Again, look at the reactants and products. You have one reactant, but you have two different products at the end. So it is a decomposition reaction because you're breaking apart a single molecule into multiple products. So again, that's why it is a decomposition reaction. All right, back to our lecture. So again, enzyme names typically end with ASE, not always. And again, remember, enzymes are not consumed by the reactions. They do not become part of the reactants or products. So the thing is that these can be used up to speed up both synthesis and decomposition reactions. That's why I use that analogy with the stapler and stapler remover. It's the same reactants and products both in either side, but they're going different directions, and it's like one is a synthesis reaction, the other is the opposite decomposition reactions. When we get to metabolism, and especially if you go into biochemistry, you'll see a lot of enzymes are kind of in this pair. One builds up, one breaks down what was previously built up. All right, so polar covalent bonds. So remember that polar covalent bonds, what you have here is an unequal sharing of electrons right here. So when you have unequal sharing of electrons, remember this causes a slight negative charge toward the that's on the atom that holds on to the electrons a little more than the other atoms. So we did talk about hydrogen bonding. Now let's talk about water solubility. So things that your cells are mostly water, approximately 70%. Now your body, so depending if you're male or female, and also depending on your age as well. But again, so don't worry too much about exact values at this point. Again, it depends on also whether you're very muscular or you have a lot of adipose tissue, or whether you're male or female. So females tend to have, like the average adult female, about half the body is water at 50%, and in adult males, about 60% is water. On average now. So things that chemicals need transport throughout your body, and the thing is that water is the main carrier of chemicals in your body. So how do chemicals go from one place to the other? Most of your fluids inside your body, these are all water-based. So then we have to talk about solutes and solvents. So it's going to be like, if you're taking chemistry, you probably already know these. So solvent is a substance used to dissolve other chemicals. This is the chemistry definition. It's very general. But the thing is that solvents, when we talk about this in physiology, pretty much we're always talking about water. I mean, it may be in some physiological papers when we're talking about substances that dissolve in fat and cholesterol and triglycerides, then we might talk about that. But when I'm talking about solvents in this class, pretty much I'm always talking about water. Now solutes, this is what's being dissolved. So again, they sound very similar, and the spelling might look similar to some of you, but they're definitely different. One is the liquid that's doing the dissolving. The other is something that's being dissolved in that liquid. And this is what we have here. So here we have a solution. So solution is a solute dissolved in a solvent. So we have here sodium chloride being dissolved in water. So again, water here is the solvent, and then the solute is sodium chloride molecules in this example. Or in this part right here, again, the solvent, that's the thing doing the dissolving. That's water. That's dissolving glucose, which is a simple sugar. So glucose would be the solute in this example here. Now, again, so this is crystalline sodium chloride. So what do we have here? Then remember that, again, this is why I bring up those polar covalent bonds. So again, there's a slight negative charge on the oxygen atoms, right? Because oxygen atoms, they like to hold on to the negative electrons a little longer. Therefore, on average, they have a slight negative charge. So which atoms are they going to attract? The sodium or the chloride ions? Again, opposites attract. So negative attracts positive. So again, this is what I'm showing here in this cartoon, crystalline. Say you take a salt crystal and just throw in water. So what happens is that the negative parts of the water molecule, due to those polar covalent bonds, these attract the sodium ions, because again, negative attracts positive and vice versa. So they form what you call a hydration sphere. So notice that these negative parts of the water molecules are kind of surrounding this sodium ion. And what happens if you repeat this over and over? Well, again, remember that with the water molecule, you have the slight negative charge on the oxygen atom, but you also have the slight positive charges on the hydrogen atoms. So those slight positive charges can also attract the chloride molecule. So here we have positive attracting negative. So the thing is that, what do you notice about this sodium chloride crystal? As this process repeats over and over again, you form these hydration spheres right here. You're going to get this initial salt crystal dissolving into water. It's all due to those positive and negative charges. Again, this is why it's important to know that electrons have a negative charge. If they didn't have that negative charge, how would you get the charges to drive this whole thing? So again, it's like hydrogen bonding is very important in not only the properties of water, but also common misconception. Polar covalent bonds are not the same thing as hydrogen bonds. So hydrogen bonds refers to these partial positive and negative charge attractions, whereas polar covalent bonds are contained within each water molecule. They're not going between these different water molecules. Again, covalent bonds are different from hydrogen bonding. So there are other polar covalent bonds. Is it just water? No, the thing is that other molecules and other chemicals can also have polar bonds as well. Another atom that can make a polar covalent bond is nitrogen. Nitrogen can cause charges and again partial positive and negative charges. And fluorine, this is a little more advanced topic, but fluorine can cause polar covalent bonds and partial positive and negative charges as well. If you're going to pharmacology or medicine, this becomes a little more important because a lot of drugs do have fluorine atoms to help them form polar covalent bonds and also in just form bonds with other substances as well. Okay, so then we have hydro so let's end on this part. So hydro, again, remember, I love prefixes and root words. Why? Because as you build a bigger vocabulary of them, if you encounter new words and medical terms, you might be able to make a good stab if you have a strong base of root words and prefixes, suffixes, and root words. So hydro refers to anything water related. So the funny thing is the thing is that with hydrogen bonds, you might think it's just hydrogen atoms, it's just water. But the thing is that it comes from that root word. Philic means something that's liking or loving, of affinity or preferring. So if you have someone that's like a bibliophile, they like reading books. If someone's an audiophile, they like listening to music. Or if someone's a winophile, they like drinking wine or something like that. So phobic is the opposite of that. So something is a fear, repulsion, or avoiding. So if you have someone who's like claustrophobic, they're afraid of enclosed places, right? Or if they're acrophobic, they're afraid of high heights and high places. So the thing is that phobic refers to a fear. So when we have something that's hydrophilic, that means it's water loving. It likes associating with water. Just like we saw sodium chloride dissolving in water, sodium chloride is a hydrophilic, or the sodium and chloride ions are hydrophilic substances. Whereas the hydrophobic, this is water fearing. So when you have something that doesn't dissolve easily in water, like cooking oil, or if you have like Crisco, can you easily throw that into water and expect it to dissolve? Not really. So it doesn't really like to mix around with the water and form those hydration spheres. So hydrophilic versus hydrophobic. Something that's hydrophilic will easily dissolve in water, whereas something that's hydrophobic doesn't easily dissolve in water. And actually, if you swap out hydro and put lipo refers to a fat or an oil. So if something's lipophilic, like a drug, that means it dissolves easily in fat and oil. But if it's I don't really hear the term lipophobic used often. But say it doesn't dissolve in fats or oils, or that would be a potential. I have to actually look that up. I have to look up whether lipophobic is actually really used. But you do see hydrophilic. Sometimes you see hydrophobic and lipophilic used interchangeably, but they're actually not the same. Anyway, so hydrophilicity and hydrophobicity. Does it dissolve in water? Does it not dissolve in water? That's pretty much the layman's terms of an explanation of this. And we're out of time, so I'll see you all on Wednesday. Take care and stay healthy, all right?